Today we're going to move on to the next topic, which is forces and Newton's laws. We've got to understand the concept of the force, understand and use Newton's first law. Newton's first law says that a particle that is at rest or moving with constant velocity will remain at rest or moving with constant velocity until acted upon by external force. So basically, if something is at rest, and it's just sitting there at a table, it's going to carry on sitting up there on the table, not going to move until some external force does something. And likewise, if something is, let's say, falling at a constant velocity, so it's not accelerating because acceleration due to gravity and air resistance are sort of cancelling each other out, it's a perfect constant velocity, then it's going to remain at constant velocity until something external happens, which is likely going to be hitting the floor. Okay, so there's the two different ways that Newton's first law can be used. We've also got to be able to understand vector notation, but as far as I'm aware, you've been doing this in pure maths, so this shouldn't be an issue. But i's and j's are just like your x coordinate and your y coordinate, how far across and how far up something is. And the different sorts of forces we're going to look at is weight. So there's a difference between weight and mass. Mass is how many kilograms something is, and force is how many newtons something is. So weight in general is going to be your mass times gravity, because that's usually what's happening with weight tension. So if you sort of pull something tight, there's like a tension force in the string, thrust. So if a rocket goes upwards, it's got thrust, compression. So a hydraulic press crushing something, it's got a compressive force on it. Normal reaction. So that basically means if something is sat on a desk, then gravity is acting on it. Okay, so you think to yourself, well, hang on, if gravity is acting on it downwards, then why isn't it just moving down? And it's because there's a reaction force from the desk pushing it back up so that it's at rest, and it's called normal reaction because if something's sat flat on the desk, then the reaction force will be going straight up, which is 90 degrees or normal to the desk. Friction, so if you're sort of dragging something along the ground, then it's going to be slowed down by friction. Driving force, which is the engine of the car is driving something along, just to take it literally. There's other ways of doing it, and that's pushing it forwards. So there's all those different sorts of forces. And it says here as well that we've only got to have a basic understanding of friction. Okay, so you just got to know that it opposes the direction of motion. You don't need to worry about a coefficient of friction because depending on how rough or smooth the surface is, certain things can act in certain different ways. And so we've just got to have a basic understanding that it just opposes motion. Okay, so that's the scheme of work. Let's move on to have a look at some of the topics. So first example is a really quite basic one. It's a block of weight W is being pulled to the right by a force P along a rough horizontal plane. Draw a force diagram, shows all the forces acting on the block. Okay, so let's look at some of the words here. So weight, not mass, weight. It's being pulled to the right by a force P across a rough horizontal plane. So when it says rough, that means there is friction. If it said smooth, there would be no friction. And it says horizontal, which is across. So it's going to have all four different things on there. It's going to have weight. It's going to have a reaction force going upwards. It's got the driving force, P, and it's got friction, F. So you see how here the driving force is in the middle of the object, and friction we put at the base to show that it's between the object and the surface that force is acting. It wouldn't quite be right to say it's going from the middle. Okay, and if all the forces are balanced, then it's in equilibrium. There's nothing to say here that's in equilibrium. It's going to be in equilibrium vertically because it's not moving vertically, but if it's moving horizontally, it could be speeding up or slowing down. It doesn't have to be in equilibrium. Okay, so we've already gone through what Newton's first law is. It's written out again there. And we've got to understand a few bits of terminology. So when there's more than one force acting on an object, you can resolve the forces. So resolve means, well, let's just see what the result is. If there's 10 newtons going one way and 5 going the other way, then the overall result would be 5 in a certain direction. Okay, and that would be called the resultant force. So you resolve forces to find a resultant force. You have got to think about positive and negative things, because we have got velocity, so it's not speed, which means if it was going 10 meters per second but in a circular sort of motion, then it'd be changing direction and the velocity wouldn't be constant really. And in your answers you can use the letter R for resultant, and we've got an arrow to indicate what direction it's going in. Okay, so we're only dealing with things in horizontal or vertical direction. If stuff goes diagonally, then you've got to use a bit of trigonometry to figure out, well, how much that's acting vertically and how much it's acting horizontally, but we'll leave that for A2. And so if there's a resultant force, then it's going to cause the object to accelerate. Okay, so if there's a resultant force, then it's not going to be going at a constant velocity. It'll just be accelerating from that point until something else happens. So, new example. Diagram shows forces acting on a particle. Draw a force diagram to represent the resultant force and describe the motion of the particle. So, we've got 20 in this direction, 20 in this direction. They balance. You've got 30 in this direction and 10 in this direction. So, 30 take away the 10, you're going to have 20 going upwards, and it's going to be accelerating upwards. If you say that it's moving upwards, or it's moving at a constant velocity upwards, even worse, it's not true. You've got to say it's accelerating upwards. It's getting faster and faster and faster upwards, because that's where the force is. Okay? Right, so what I've got here is I've just cut a few questions from this exercise that I'd like you to have a go at. So I've got 5 easy ones and a couple of hard ones on the next slide. So they're just about force diagrams, and it should be easy enough. So what I'm going to do is I'm going to suggest that you pause the video now, but for no more than 10 minutes. If you haven't finished these after 10 minutes, then just move on, because there's more of this lesson to go. Okay, so pause the video now, and if you either run out of time or you finish the question sooner than 10 minutes, then unpause it and I'll move on to the next questions. Okay, and here are the more difficult questions. So again, you don't want to be spending any more than 10 minutes on these couple of questions, because we've got other things to do today. So pause the video now, but for no longer than 10 minutes, have a go. And answers to the previous questions and these questions will be in the back of your textbook. It's exercise 10A. And if there's any, I'm not going to go through them now because I've gone through a couple of examples. But if there is anything you want to know in more detail, then you can just sort of ask me in the chat or by email. Okay, so pause it now. Okay, so the other thing we're going to look at today is vector notation, so I and J notation. We've got column vectors as well. So if you've got a column vector, the top number is the I, the bottom number is the J. It's like vertical coordinates. And if you think about it, then anything which has got I and J notation, you could draw a little diagram, and the I's would be how far across it's going, and the J's would be how far up it's going. And just like the previous exercise, you could just turn it into that sort of diagram and work out resultant forces that way, just by seeing how things resolve horizontally and vertically. So just comparing the I components and the J components. And if there's 0i and 0j, that means there's zero resultant and it's at rest, or it is moving at a constant velocity. Okay. Again, I'm assuming you've got a basic grasp of this, which is why I'm not going into too much detail on it. But if you do want to know more about it, then again, let me know, and I'll go over it in more detail. So, an example, we have got these different forces acting on an object. We know it's in equilibrium, which means we know that the resultant force is going to be 0. Find the values of A and B. So we've got numbers here, and we've got A and B there, so we don't know what the numbers are. So we just got to resolve the i's and resolve the j's. So the i's, there's 2, 4, minus 3, and A. So combine those, and we know it's got to equal 0 because it's in equilibrium, which means that A is going to be negative 3. And combine the b's, you've got 3, minus 1, 2, and B. Combine those, you're going to get that B is negative 4. Okay, and it's as simple as that. Next example. So in this question, I represents a unit vector due east, J represents a unit vector due north. So it's just basically saying north is up and up this way, east is this way. So it is just like your x and your y coordinates. Unit vector means that if it just says I, that's just a 1 across. And if it says j, that's 1 up. And if it says 2i, that's 2 across, so on and so on. So we've got a particle that begins from the origin, so it's 0, 0. It's acted upon by 3 forces, 2i plus j, 3i minus 2j, and minus I plus 4j. Find the resultant force. So just add the i's, and that'll give you P. Add the j's, that'll give you Q, and you can give the answer in that form. Work out the magnitude and the bearing of the resultant force and describe the motion of the particle. Okay, so first one is going to be easy enough here. We've got the 2, the 3, and the minus 1 gives you 4, and the 1, the minus 2, and the 4 gives you 3. So the next one. So when we want the magnitude, we can see this diagram here. It's going 4 east and 3 up. Okay, so it's not going to be just moving in a sort of step formation. It's not going to go 4 across and 3 up, then 4 across and 3 up, and 4 across and 3 up. It's not going to be moving purely across. It's not going to be moving purely up. If you think about it, if it's going across and up, it's going to be sort of diagonally up in some respect. It's not going to go a perfect 45-degree diagonal because these are different forces. It's going to be a little bit more towards the horizontal. So to find it out exactly, if we just reposition this, because normally this arrow here, you'd think about it being here. If you just reposition it, then this forms a right angle triangle. And if you do Pythagoras on that right angle triangle, you can find out the size of that force is 5 newtons. So it's 5 newtons in this diagonal direction. And how far the diagonal direction is, if we use just right angle triangle trig, SOHCAHTOA, then you're going to get that this is going in the 36.9 degrees, this angle is. But think about bearings. Bearings are clockwise from north. So here's your north line. Our angle down to here would be 53.1. You've got to stick a 0 in front because bearings have to have 3 digits. So it's a bit of a recap of GCSE stuff there with bearings, but you're capable of it. And describe it, we've got to say, well, it's going to be accelerating at this direction with this force of 5. Okay, so let's go back and look at the scheme of work, because obviously we know there's no WJC proper textbooks for these. We're using the Edexcel ones. So if we just compare what we've just done there to what the scheme of work says. So, learners only require basic understanding. What does it say about horizontal and vertical? So, coefficient of friction not needed. What does it say? about horizontal and vertical. Okay, so it doesn't say anything there about not having to work out resultant forces and things like that. Okay, so we don't need to say that that's this is it. This is where it said it. In this section, you'll only resolve forces that are horizontal and vertical. So it is from Edexcel. It says that, not from WJC. And WJC, there's no mention here of working out those diagonal ones. So working out these resultant ones is well within our capabilities. Okay, so sorry about the confusion. I just wanted to check that this is something you need to know. And yes, it is something you need to know, because we've started off with horizontal and vertical ones only, and we've resolved it to be diagonal force. You're not going to start off with diagonal forces where you work out horizontal and vertical components. That's what's in A2. Okay, so that's the examples for today. This is the exercise I want you to have a go at properly. It's sort of attached below. I know you spent 20 minutes working on the other questions, or perhaps you haven't finished sooner, but the rest of the time you've got for this, I'd like you to complete this exercise. And as usual, send me your answers and ask for help if you need help with anything at all.